Welcome, grade 9 learners. I am your host and your very enthusiastic guide for today. Okay, let's get right into it. In today's explainer, we're unpacking the incredibly dynamic science of plate boundaries. We're going to look really closely at the actual forces that shape the ground beneath our feet, build massive mountain ranges, and trigger some seriously powerful natural events. It's going to be a fun one.
To get us started, I want you to consider this fundamental question. Why is the Earth's surface constantly changing? I mean, it might look perfectly still when you look out your window, right? But beneath your feet, our planet is completely dynamic. Imagine the Earth not as a solid, unbroken sphere, but as this giant, moving puzzle. And the most fascinating part? The puzzle master is still actively moving the pieces around. We are going to build this puzzle piece by piece today to understand exactly how our world works. Here is our roadmap for today's grade 9 science lesson under the MATATAG curriculum. We've got 1. The Earth's moving puzzle. 2. Convergent, the colliding plates. 3. Divergent, the spreading plates. 4. Transform, the sliding plates. 5. Features versus events explained. And finally, 6. The Philippine Ring of Fire. All right, let's dive into part 1, the Earth's moving puzzle.
So to really understand plate boundaries, you first need to understand the lithosphere. Basically, this is the rigid outer shell of the Earth, but it's not one solid piece of rock like an eggshell. It is broken up into large and small pieces called tectonic plates. Think of these tectonic plates as giant jigsaw puzzle pieces. But instead of just sitting there flat on a wooden table, these pieces are floating on top of a really hot, semi-fluid layer of the Earth's mantle right beneath them. And here is a totally crazy fact for you. These massive plates are moving right now at just about the exact same speed that your fingernails grow. How wild is that? Now, you might be wondering, what on earth is strong enough to push continent-sized pieces of solid rock around? Well, the answer is extreme heat. Deep inside the Earth's interior, there are these things called convection currents. Just picture a pot of thick soup boiling on a stove. The hot soup rises to the top, it cools down a bit, and then it sinks right back to the bottom, right? Well, this exact same continuous cycle happens with the semi-fluid rock in the mantle. This hot rock is constantly heating up, rising, cooling down, and sinking back again. These convection currents act as a massive hidden engine. They are literally the driving force that slowly but surely drags and pushes these massive puzzle pieces around the surface of the Earth. Moving on to part 2, Convergent, the colliding plates. A convergent boundary is simply a region where two tectonic plates are moving directly toward each other and colliding. Imagine a slow-motion, super high-stakes crash. But what actually happens after the crash? Well, the outcome of this collision depends entirely on the specific types of Earth's crust that happen to be involved. So, the absolutely crucial point here is understanding the difference between the two types of crust we have. On one hand, we have oceanic crust. This is the crust underneath our oceans. Oceanic crust is mostly made of really dense basalt rock, which makes it heavy, so it naturally tends to sink. On the other hand, we have continental crust. This is the land we actually live on. Continental crust is much thicker, sure, but it is made of lighter rocks like granite, meaning it tends to float on top. Keep these weights in your mind because they dictate exactly what happens when these massive plates finally crash. Let's break down step by step what happens when an oceanic plate collides with another plate. First, boom, the plates collide. Because that oceanic plate is much denser and heavier, it is literally forced to sink beneath the other plate. This sinking process is called subduction, and it creates what we call a subduction zone. As that heavy plate gets shoved deep into the super hot mantle, it actually begins to melt. That newly melted rock, or magma, then rises right back up to the surface. This entire process is exactly how incredibly deep ocean trenches, like the famous Mariana Trench, are formed, right alongside vast chains of volcanoes known as volcanic island arcs. But wait, what happens if two continental plates crash into each other? Remember, continental crust is light, so when these two collide, neither one is quite dense enough to subduct or sink into the mantle. Instead, it's kind of like taking a flat piece of paper and pushing the ends together on your desk. The crust simply crumples, folds, and is forced straight upwards. This epic upward crumpling is what creates massive mountain ranges, literally just like the Himalayas. And because there's no subduction happening and no melting rock, there are absolutely no volcanoes formed here, just towering massive mountains. Which brings us to part 3, Divergent, the spreading plates. At a divergent boundary, two tectonic plates are actually moving away from each other. They're separating.
This constant pulling apart creates intense tension and literally rips open a gap in the Earth's crust. And nature hates a vacuum, right? So magma from the mantle rushes up to fill this newly created gap, cooling down and solidifying right there at the surface. Because it's continuously creating new rock, this is often called a constructive boundary.
When plates diverge, they leave behind some very specific physical formations. If this spreading happens deep underwater, it creates mid-ocean ridges, which are essentially massive underwater mountain chains. If this pulling apart happens on land, it creates incredibly deep rift valleys, like the East African Rift that we can see today. In both cases, this incredible geologic process is quite literally manufacturing brand new oceanic crust for the Earth. Next up is part 4, transform the sliding plates. Okay, so a transform fault boundary occurs when two tectonic plates slide past each other horizontally, side by side. Unlike the other boundaries we just covered, they aren't crashing into each other and they aren't pulling apart either. Because of this, at transform boundary, crust is neither created nor destroyed. It's just a constant, relentless, grinding, scraping motion. But here's the catch. As these massive plates scrape past each other, they definitely do not slide smoothly. They get stuck, and that intense friction builds up incredible, unbelievable amounts of stress and energy over decades or even centuries. And then, eventually, the rock just snaps. All of that stored energy is suddenly released at once. This is exactly what triggers powerful earthquakes. The San Andreas Fault in California is a textbook example of a transform boundary. The plates slide, the tension breaks, and the earth shakes, and notably, without any volcanoes popping up. Let's clear up a really common misconception in Part 5, Features versus Events Explained. You'll often hear these two terms used in science class, but they mean very, very different things. Geological features are the permanent physical landforms left behind by plate movements. Think of them as the permanent scars on the Earth's surface, the big mountains, the deep ocean trenches, the rift valleys. Geological events, on the other hand, well, those are the active, real-time processes. They are the actions happening right now because of the plate movement. Things like earthquakes shaking the ground, massive tsunamis rolling in, and explosive volcanic eruptions. Let's put it all together. This right here is basically your ultimate cheat sheet for the lesson so far. Convergent plates move toward each other, resulting in mountains, trenches, and volcanoes. Divergent plates move away from each other, resulting in ridges, rift valleys, and new crust. And transform plates slide past each other, resulting in fault lines and massive earthquakes. Pretty simple when you lay it out like that, right? And finally, Part 6, the Philippine Ring of Fire. If you live in the Philippines, or if you've ever just wondered why the country is so prone to natural disasters, well, geology has the answer. First off, the country lies squarely on the Pacific Ring of Fire, which is this massive horseshoe-shaped region in the Pacific famous for frequent earthquakes and intense volcanic activity. The Philippines is quite literally being squeezed by the interaction of several massive plates, the Philippine Sea Plate, the Pacific Plate, and the Eurasian Plate. Because of this squeeze, it's surrounded by active subduction zones, which create beautiful but extremely dangerous volcanoes. Add in major transform fault lines slicing right through the country, like the West Valley Fault, and you essentially have a perfect recipe for extreme geological events. And honestly, this is exactly why this topic isn't just something you memorize for a test. Ultimately, understanding these plate boundaries helps us predict hazards and truly appreciate the dynamic nature of our planet. Knowing exactly where fault lines and subduction zones are allows communities in the Philippines to engage in serious disaster preparedness. It tells us where it's safe to build our homes, and it explains why participating in those earthquake drills could quite literally save lives. Okay, let's lock today's MATATAG curriculum lesson into our memories with a really quick recap. The Earth's lithosphere is made of puzzle-like plates that are driven by mantle convection currents. When they meet, three things can happen. Convergent boundaries involve colliding, causing subduction zones, or building massive mountains. Divergent boundaries involve spreading, creating new crust and underwater ridges. Transform boundaries involve plates sliding past each other, which builds massive friction and triggers earthquakes. And remember, features are the lasting landforms, while events are the sudden geological actions. Before we wrap up this explainer, I've got a profound question for you to chew on. These tectonic plates are moving right now, shifting just a few centimeters every single year. Knowing what you now know about colliding, spreading, and sliding, what do you think the Earth's map will look like 10,000 years from now? Are new oceans going to open up? Will new mountains dwarf the Himalayas? It is a fascinating, continuously moving puzzle that is far from finished. Thank you so much for joining me today. Stay curious, and I'll catch you next time.